Okay, great. Thanks, Nick. Great to be here with you. Wasn't sure exactly what the timing of that beginning was, but Ben Eggleton, I'm in Sydney at the moment. Really delighted to be with you for this really interesting discussion. I can see my colleagues on the screen, and I know there are others joining for this really interesting discussion. Before we do begin the proceedings, I would like to acknowledge and pay respect to the traditional owners of the land. I'm in Camperdown on the University of Sydney campus right now, which is the land of the Gadigal people of the Eora Nation. I presume you are in your own local home probably, so ask you to pay respect to the lands that you're on. As we share our knowledge, teaching, learning and research practices within this university where I am at, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. It is worth remembering that the Aboriginal people have been managing the land in Australia for 60,000 years. And as we have our conversation, we might just reflect on the lessons that we can learn from them as we think about sustainability for the next generation. So it's great to be with you today for what promises to be a fascinating, rapid fire conversation on a really key issue that's very timely in the media. Nick, if you can just share the slides, I'll just give a bit of an introduction to set the scene. Okay, so there are a number of objectives that are overarching for the conversation. It's clear that technological innovation is central to measuring, monitoring, adapting to and mitigating climate change. This is a discussion specifically focused on the opportunities that lie at the intersection of climate change and smart sensing innovation. And more specifically, what we're going to tease out in this discussion is what role can smart sensing play in responding to the global net zero agenda, and more locally, the New South Wales Net Zero Plan. And I'll return to those specific initiatives at the end of my slide deck. So in the discussion today, we have the New South Wales Smart Sensing Network ambassadors, leading academics at the NSSN universities, working at the leading edge of smart sensing science. And we asked the ambassadors to invite their colleagues who are climate change experts from the member universities to join us for a dialogue, as I said, at the nexus of smart sensing and climate change. So I don't need to reiterate, but the NSSN is a member-based organisation with the 7 universities listed here on the slide. And as mentioned, we've got representation from these 7 outstanding universities in the conversation today. So a little bit more specific context. Obviously, this is clearly in the context of the COP26 meeting that is happening next week. And of course, we have been following in the media and some of the performances from our various political leaders. Without really belaboring the point, the clear goals for COP26 are to secure global net zero by 2050 and keep the 1.5 degree target in reach, adopt to protect communities and natural habitats. We'll hear some examples on that this morning, mobilise, finance and work together to deliver. The UK presidency missions are also listed there, really reiterate those same agendas. So a bit of scientific context and why it makes sense to have a conversation about smart sensors. Well, simply speaking, you can't manage what you don't measure. Climate and economic policy requires rigorous data sets and reliable modelling, and that needs to be done at a regional level, and sensors play a vital role in those areas. And as mentioned, and as has been highlighted by the Prime Minister, technological innovation is going to be critical to achieving the global net zero agenda. So the final point I wanted to make on this slide is that there are already a number of global initiatives that represent potential platforms for NSSN to be involved in. One that I'm familiar with is the Global Environmental Measurement and Modelling Initiative. This has actually been around for a few years, and I've been involved in various conversations and presented at various workshops. It's interesting that when this was put forward about 4 years ago, there was a discussion around a number of Australian universities about Australia being a member of this network, and there was consensus at the time that there wasn't going to be an appetite, which was more of an indication, I think, of the political appetite for such initiatives. And I think it's fair to say that we have, as a nation, matured our perspective on the issue. So we're going to look at and hear from thought leaders across a number of different areas, sectors. It's going to be a fascinating, very broad perspective on where smart sensors may or are playing a role. This is a bit of work that one of our theme leaders put together as a potential perspective, just to highlight really the landscape. Sensors are playing and will play a vital role in sensing pollution, the atmosphere as it relates to methane, for example, LIDAR, weather balloons, energy monitoring, remote sensors, and of course, more generally, sensors that play a role in photosynthesis and in plant stress monitoring. So as much as we have the COP26 climate change agenda, which clearly provides a global context for this conversation, there are also the very well-established UN sustainability goals that you're all familiar with. And in fact, we know, and we've heard from you as we talk to your leadership over the last 6 months as part of a stakeholder consultation, that the sustainability goals are really important to universities, to DVCR strategies. We've looked at the UN sustainability goals and decided that these 6 really are the priorities, at least around climate change and smart sensors. So we'd like to take some consideration of these UN sustainability goals as we hear your presentations, as we have a conversation, as they relate to these specific objectives. And so the final point is just to reflect again on the policy context. So it's worth noting that New South Wales is on the front foot, has been on the front foot for a while, for various reasons. I think our government has been very proactive. There is the New South Wales Government Net Zero Plan, which aims to deliver 50% cut in emissions by 2030, net zero emissions by 2050. And there are already specific initiatives that target energy consumption, electric vehicles, hydrogen. We've heard a lot about hydrogen, primary industry, circular economy, a lot of investment in circular economy and tech innovation. And of course, we also have the Commonwealth Government putting forward its own initiatives. And ScoMo, our Prime Minister, it seems to be dragged along reluctantly, but is on board, and the country is really standing up for the first time, I think, a commitment to this important issue. So I think, Nick, that's sort of a bit of a perspective from me, and I think I'll hand over to Julian to give some very specific objectives for the session today.
Thank you very much, Ben. And I'm delighted to have joined you recently as an NSSN co-director. For those ambassadors and researchers I haven't met yet, as well as those I have, let me extend also a very warm welcome. And I really look forward to hearing about your research and getting to know you all. We're very fortunate to have 14 experts from both smart sensing and climate change here today from across our member universities, because there's a huge potential and need for collaboration across these disciplines. So each researcher will speak for 5 minutes on how their research contributes to smart sensing and climate change. And then at the end, we'll hold a 30-minute discussion to build further on the points that have been made. As you can see from the slide that Nick's shared here, the intention is to create a manuscript from this event, a white paper, a thought piece, and hopefully also the beginnings of some new research projects. I want to finally note, probably on the next slide, that the theme for this roundtable overlaps significantly with 4 of NSSN's grand challenges. Those are bushfires, smart places and buildings, mining and water, and also that the NSSN Grand Challenge Fund is opening soon for submissions. Before we proceed, I just do need to mention that we're on a very tight schedule. So for each speaker, there will be a bell at the 30-second mark. And I'd like to ask everyone to please conclude within their 5 minutes. There's no need to be disappointed if we run out of time because your abstracts all appear in the full roundtable program. And similarly, in the interests of time, I'll only introduce the names of each speaker and their university, noting that the full biographies also appear in the program. So without further ado, I'd like to welcome, please, Professor John Close from the Australian National University.
Thanks, Julian. I hope everyone can hear me. Okay, yes, there's a thumbs up. Thank you. First of all, before we start, I'd like to tell you what I know and what I don't know. So I'm a physicist, quantum sensor person, but I've been working in a significant collaboration with hydrologists, with Bayesian inversion experts, and also with GRACE satellites, so satellite-based gravitational measurements, to ask the question, can we elucidate, can we map and monitor Australia's groundwater resources using gravity and also using algorithms to invert that signal and tell us what's happening under the ground? So let's map out the problem. Here. So clearly Australia is an arid country. Australia's water resources are critical, both economically, environmentally, national security. It cuts across all these areas, and groundwater is particularly important. Our groundwater resources are not particularly well understood. Enormous amount of research has gone into them, but my hydrology and water management friends tell me that, and some of you may know this much better than I do, tell me that Australia's best measured and monitored reservoirs have a hole in the water budget as big as 20% or more. In other words, you account for all the inflows and all the outflows, and 20% of the water, where's it gone? Presumably it's gone into groundwater. Not only is it important to find out where it's going and where it's stored, but when water is released upstream to supply farmers, I also understand that in many cases, the water never makes it to where they want it to make it to, because it's presumably goes into groundwater recharge. Gravity is an interesting new tool, and I'll mention why it's new in a minute, new tool to perhaps map Australia's groundwater resources. The basic principle is straightforward. Dry land is less dense than wetland. Water goes in, local density goes up, gravity goes up. If you now make terrestrial measurements of gravity with a stable sensor, you can map the gravitational changes as a function of time and as a function of position. Now, of course, this is already done using GRACE satellite imagery. So gravitational sensors on satellites measure Earth's gravitational field and determine what's happening with water movement and glacial melt and so on. But these are large length scales. 200 kilometers is the smallest spatial resolution. We're looking to use gravitational mapping to fill in the shorter length scale information. So tens of meters up to the 200 kilometers that is possible with GRACE. So fill in that important length scale and also time scales. So the question would be, why now? Gravitational sensing has been around for many years, and there are excellent commercial devices on the market that have excellent short-term sensitivity. What's new is that in the next few years, we'll see sensors coming out of laboratories which have not only equal or equivalent short-term sensitivity, they have tremendous long-term stability, and they have inherent accuracy. And I'll come back to that in just a minute. These are new kinds of sensors. They're atomic sensors or atom light sensors, if you like, and they're particularly suited to questions like groundwater resources, because the signals from these resources come in on very long time scales. If you don't have a stable device, you'll never be able to see those signals. All right, so this is the why now. So the problem is groundwater resource mapping, monitoring, and management. That's the problem. The potential solution is gravity mapping, and the why now is that these quantum sensors are coming online now in our labs and coming into the commercial market. Very quickly, I think I have a minute left on my timer, Julian, so I'm watching it too. Just a quick word about why these sensors are different. So traditional sensors are masses on springs, highly engineered, beautiful devices, capable of measuring gravity to about 1 part in 10 to the 8 in a 1 second measurement. No accuracy at all. They'll tell you if gravity went up and down. They drift because the spring can drift. Our devices are a laser beam, which forms a ruler, vertically oriented, a mass, which is a bunch of cold atoms at very low temperatures, and we let those masses fall under gravity in ultra-high vacuum. The distance they fall is related to local gravity, underpinned by universality of free fall, verified to 1 part in 10 to the 15. The lasers are locked back to the definition of the meter, and the time is locked back to the definition of the second. This is where the inherent stability comes from. These are moving now from lab into field deployment. And Julian, I see my time is up. I will stop there.
Thank you very much, John. I'd now like to welcome next Associate Professor Marta Yebra, also from the Australian National University.
Thank you, and I apologize I joined a bit late. Just before I start introducing what we are doing at the ANU with smart sensing for bushfire prevention, response, and mitigation, the main point here is that the most recent IPCC report warns that the frequency and the severity of bushfires is likely to increase because of more frequent coincidences of heat waves, droughts, and fire weather. So this will definitely make it difficult to achieve some of the sustainable development goals that we are discussing today. So for example, in the 19 and 20 bushfire season, this season came after the second hottest year on record with multiple record high temperatures and heat waves events that led to an unprecedented soil and fuel dryness that created the perfect conditions for ignitions to quickly become uncontrollable. And as we all suffer at some extent, this led to significant losses in lives and biodiversity, as well as economic, health, and social costs, and a good release of CO2 and other greenhouse gases into the atmosphere. Current approaches to prevent, detect, and rapidly extinguish bushfires before they become uncontrollable are not always effective during these extreme weather conditions. Therefore, we need urgently to accelerate the development and implementation of modern technologies to quickly detect and extinguish bushfires well ahead of future catastrophic bushfire seasons. So at the Australian National University, we are undertaking multidisciplinary research to achieve that ambition with 6 programs covering from prevention to suppression. So today I'm going to focus on 2 of the 6 research programs, as they are more heavily relying on smart sensing technologies. So firstly, the Fire Prevention and Risk Reduction Program with OzFuel is a program that is developing an Australian macro satellite low Earth orbit mission with an infrared sensor that will be able to identify the settings for catastrophic bushfires events by knowing where there is a continuous cover of fuel dry enough to facilitate fire to ignite and behave extremely. A recent study that was commissioned by Geoscience Australia, and you can download online, I can share the link later on, present the feasibility of the OzFuel satellite to monitor Australian fuels from space every 6 to 8 days during the early hours of the afternoon. That is when the vegetation is more stressed and can be more easily ignited, and at a spatial resolution of about 50 meters, which is adequate for bushfire management operations. So the second program I wanted to focus today is the core of the ANU Optus Bushfire Research Center of Excellence, is ignition detection with an integration of an evaluation of different detection methods and technologies to determine the scenarios in which each technology is more effective. So the multi-sensor and platform solution include geostationary satellites that provide constant surveillance across Australia, but they may not be able to identify very small ignitions given the current spatial resolution these sensors have. Includes low Earth orbit satellites that, given their better spatial resolution, they can detect smaller fires. It includes a drone network that can achieve fast identification, location, and verification of bushfire emissions due to lightning strikes during a thunderstorm. And then cameras on towers and on ground sensors that, although they have limited spatial coverage per camera or sensor node, they can be strategically located in areas of elevated risk or conservation value, or in the case of the on-ground sensor, they can also be located in areas that are not visible by the cameras. So to sum up, major bushfires are a concern around the world and can compromise the achievement of some of the sustainable development goals. So we need to drastically reduce our emissions to maintain the 1.5 degrees target. So further warming doesn't even boost further the bushfire risk, but we also need to accelerate the implementation of this technology as soon as possible to ensure that we are ready to stop any catastrophic bushfires that may come.
Thank you very much, Marta. I'd now like to welcome Dr. Nushan Nasiri from Macquarie University.
Thank you, Julian. So I'm going to walk you through why our team at Center of Smart Green Cities at Macquarie University believes that sensors and sensor networks have an important impact in meeting environmental degradation and global warming challenges. Sensor applications in multiple fields such as smart grids, smart buildings, and smart agriculture and farming significantly contribute to more efficient use of resources and a reduction of greenhouse gas emissions and other sources of pollutions. From smoke hanging over cities to smoke inside the home, air pollution poses a major threat to climate and health. Among gases that cause the most air pollution, volatile organic compounds, or VOCs, emissions are one of the biggest environmental problems today. When exposed to sunlight, VOCs react with other gases to form ground-level smoke compounds, which stimulate disease in plants, inhibit seed production, and hinder fertilization. The burden is expected to increase exponentially without an improvement in air pollution monitoring technologies. In the energy sector, coal power plants are responsible for nearly 40% of electricity production worldwide and responsible for a significant share of CO2 emissions. To decrease emission from the energy supply side, alternative clean technologies can be used to generate electricity, or energy can be distributed in a more efficient way. On the generation side, sensor networks enable solar energy to be generated more efficiently, and automated panels managed by sensors track sun rays to ensure that sun's power is gathered in a more efficient manner. Sensors and sensor network in smart building systems significantly contribute to energy reduction, as they can be used in multiple smart buildings applications, including lighting, shading, heating, ventilation, and so on. They estimate the energy saving due to more precise climate, air quality, and occupancy sensors at 30% compared to buildings with traditional automation technology. Sensors and sensor networks play a vital role in the increase of transport efficiency. For example, sensor technology contributes to better tracking of goods and vehicles, which might result in lower level of inventories. This can lead energy saving from less inventory infrastructure, as well as a reduced need for transportation. In the field of plant and crop monitoring, wireless sensors have been developed to gather, for example, data on leaf temperature, chlorophyll content, and plant water status. Based on this data, farmers are able to detect problems at an early stage and implement real-time solutions. Sensors contribute to real-time monitoring of variables such as soil fertility, soil water availability, and soil compaction. Through the monitoring of the soil, climate, and plants, a precise irrigation rate can be determined, which may lead to a reduced consumption of water, fertilizers, and pesticides. Both fertilizers and pesticides application affect surface and groundwater quality, quality of crops, soil properties, and non-target species. Smart grids and smart power system in the energy sector can have major impacts on improving energy distribution and optimizing energy usage. Smart housing can contribute to major reduction of energy use in hundreds of millions of things. Smart transportation systems are a powerful way of organizing traffic more efficiently and reducing CO2 emissions. Through monitoring the soil, the microclimate, and crops, it is possible to apply only the fertilizer and the pesticides crops need. All these applications have one important attribute in common. They all rely on sensor technologies and often on sensor networks. Thank you.
Thank you very much, Nushan. I'd now like to welcome Professor Michelle Weishmann from Macquarie University.
Thanks very much. So I'm a plant ecologist, and I lead a consortium called Which Plant Where at Macquarie, focusing on climate-ready plant species selection for urban greening. And I lead I'm the director of Macquarie's Smart Green Centre's Research Hub. So for my 5 minutes, I wanted to focus on the nexus of smart sensing and climate change in cities. And this aligns with the SDGs 11, Sustainable Cities and Communities, 13, Climate Action, and 15, Life on Land. So cities occupy only a small amount of the planet's land area, about 4%, but they're home to half of the world's population. And by 2050, we projected to be about 70% of global population. They also account for about 70% of global greenhouse gas emissions. So they're important, and they face considerable challenges with climate change. So increasingly, our cities will need to cope with extreme heat for the built and the green infrastructure, and also for people. And many global cities will also need to cope with reduced rainfall, which has implications for water security. So there's growing interest internationally in how our urban green areas can offer solutions to these climate change challenges. So we're seeing governments from global megacities right down to local councils developing urban forest strategies. And these are really exciting initiatives, but we need to develop tools that effectively design, evaluate, and manage our urban forests. And this is where the smart sensing technologies have a key role. So just to make sure we're all on the same page, just let me clarify. So when I talk about urban forests, I could be using terms such as green infrastructure or urban green space. It's all the same, interchangeable, and it encompasses everything from public parks, residential gardens, street trees, remnant bushland, green roofs and walls, and even stormwater management systems like rain gardens. And when we talk about the benefits that urban forests can deliver, we're talking about climate change mitigation through carbon sequestration and storage. We're talking about climate change adaptation through urban cooling. So a 10% increase in canopy cover, green canopy cover, can produce a more than 1 degree decrease in temperature on average, and on extreme days up to 6 degrees. So it's incredibly useful. And also climate change adaptation through water management. So the vegetation intercepts and retains the water in the landscape, so it helps for water conservation. And of course, urban green space has a whole lot of additional benefits: biodiversity, human health and well-being, improving the livability of our cities. So how can we use sensor technologies to ensure that we have healthy urban forests that deliver these climate change mitigation and adaptation benefits? And although the concept of smart cities is being widely adopted by governments and planners, we have smart city strategies all over the place, the potential to apply that smart technology for urban forest management has been largely overlooked. But we have all sorts of advances in data availability and remote sensing technology and wireless sensor networks, cloud-based platforms, etc., that can be used for smart urban forestry. So I think there's two main applications of smart technologies for urban forests that I wanted to highlight. The first is to monitor and manage urban forests. So that means that our urban forests are resilient to climate change and deliver the benefits that we're talking about. So we need to develop integrated sensing and management systems that monitor the urban forest and the environment, coupled with visualization and automated systems for real-time on-ground management of urban forests, for example, to deliver the water or the nutrients or the pest control that it's needed when it's needed. So we're talking about drone or satellite-based sensing to monitor tree canopy health, whether it be chlorophyll or NDVI, to monitor soil moisture, ground-based sensors to monitor environmental conditions, soil moisture, soil nutrients, air temperature, air pollution, airborne and ground sensors to visually monitor plant stress, and plant-based sensors to monitor plant health. So water use or stress from lack of water, lack of nutrients, or pests and diseases. And then the second main application is to quantify the benefits that are provided by the urban forests. We can't value what we don't measure. So we can use all of those different types of environmental and plant-based sensors to enable us to measure the carbon sequestration, to measure the cooling benefit, to measure the air pollution reduction. And we can look at them in relation to the different species that we're using, the configuration of the urban green spaces, and that will help us to develop integrated decision support systems for urban design and planning. And it will also facilitate our capacity to do natural capital accounting. So that valuation of urban forests is incredibly important. So what are the gaps and the challenges? Species-specific detection of different sorts of stresses, plant-based sensors such as those graphene-based sensors to be used for more than just water. There's a lot of work that can be done there. And then the perennial things are the battery life for sensors and automated systems, and integrating all of that data from multiple sources. So for these integrated systems, we've got data coming in from ground-based sensors, plant-based sensors, remote sensing, data from the Bureau of Meteorology. How do we put that all together and deliver them through visualization tools and decision support tools? And that's it from me.
Thank you very much, Michelle. I would now like to invite Professor Subhas Mukhopadhyay to speak, also from Macquarie University.
Yeah, thank you very much, Julian. So I'm Subhas. I work at Macquarie University as Professor of Mechatronics Engineering. Last 20 years, I am working in the area of sensors and sensing technology. Basically, I design, develop, and fabricate sensors using both MEMS, micro electromechanical systems, and in recent times, flexible technologies. The main idea of developing sensor is to make the sensor very low cost. One of the challenges what we face is that we try to make very expensive systems, and in the climate monitoring, where the areas are very large, whether we monitor air or water, we need to have distributed real-time monitoring. That means we need billions or trillions of sensors. And in order to have that, we need to make the cost as the important factor. So we need to develop very low-cost sensors. Now, always the low-cost sensor will have issues. So we need to think of the sensitivity as well as the selectivity. Once we have that and we have these sensors installed in the environment, we need to think of the effect of the parameters such as temperature and humidity. So we need to have compensations. So interfacing electronics will play an important role to make these sensors smart. And then we have to put the data in the cloud because we want the data variations with time as well as space. So we need to make this data in the cloud, and we need to introduce machine learning and artificial intelligence. These are the things to go. So basically what I'm proposing is that all the sensors, what we need to use is to be IoT enabled, Internet of Things enabled sensors. That's the way we have to have the solutions. Now I will touch few applications which I have been involved. One of the important thing is the human. When we see the UN guidelines of sustainable cities and communities, we have to address how we can address our community. Now, people living at home, and most of the time we have some kind of problems in our health. And if we make a connected health, by 2026, we can actually see the market of $332 billion. And if we have that connected healthcare system by smart sensors, we can detect the problem at early stage and we can save significant amount of money. So if these sensors are used in smart home environment, we will save a lot of money. Second thing is the water. Before me, Professor John Claus told of the gravity sensor. We are working on the same project funded by the New South Wales government in DPIE. We want to see where is all water. We are not able to know 25% water. One of the problems what we have is that this groundwater, what we are trying to save, may not be everything. We need to know rainfall, exact rainfall, and exact amount of water is lost due to evapotranspirations. So what we need is the distributed sensors which will measure real-time exact amount of rainfall and the soil properties, so that how much water is actually percolated and how much water is actually evaporated. So my group, we are trying to develop low-cost sensors for their applications so that we can have many sensors installed at the strategic point so that we know the variable properties of the soils from place to place. And that will give us much more clear indications and how much water is actually lost. Third thing what I want to touch is that in the agricultural sector, now Australia is too much dependent on the dairy. And what we know that cows, because we feed them different types of food and they actually produce methane gas. So if we can develop low-cost sensors to know that these methane gas productions, how they are related with the feeding, then we can actually, farmers can actually take appropriate actions and we can reduce the methane gas emissions. Also, we can develop nitrate sensings. Like my group, we are developing nitrate sensor for last 6-7 years, and we can develop low cost, high sensitive and selective nitrate sensors, which can be distributed in areas, and we know how much is the nitrate leaching in the groundwater. So effectively, what I'm telling is that real-time, low-cost, distributed sensor system, and they should be IoT enabled, is the way to go forward. Thank you.
Thank you very much, Subhas. I'd now like to introduce Professor Paul Dastoor from the University of Newcastle.
Good morning, everyone. A slight change of pace now, if I may. I just want to talk about some of the work we've been doing on developing actually new low-cost affordable energy and how that then relates to our interaction with NSSN. The work that we do looks at semiconducting polymers. These are remarkable materials that are electronic polymeric systems that we can develop into inks. And that means that we can deposit them and coat them as low-cost coatings using printers, large-scale manufacturing technology. So our developments at the university have encompassed work all the way from fundamental research up to large-scale implementation. And in particular, we have developed a full manufacturing pilot facility for producing large areas of certain printed electronic devices. Our interactions with NSSN, of course, have focused on printed biosensors. But a parallel stream of work that we undertake is actually focused on developing printed solar cells, being able to manufacture these energy generation systems at low cost and at high speed. Currently, we can manufacture at thousands of square meters, hundreds of square meters scale, but our target is to be able to develop manufacturing facilities that allow us to make thousands of square meters of printed solar. Where does this target in terms of the UN's Sustainable Development Goals? Of course, it targets affordable energy, number 7. And in particular, we now have partnered with a commercial entity, Gardenia Energy, and to develop the technology all the way through its complete innovation pathway. So we actually develop the ink synthesis, the solar manufacturing, the scale production, commercial installations, and in fact, recycling, all tied up with the energy economics of the technology. And of course, the unique value proposition here in terms of Australian technology is that we control the entire innovation pathway. Our demonstrations since 2017 have included large-scale installations, including installations at on roof 200 square meters of commercial installation at CHEP, in Beresfield. Last year, the first public demonstration of the technology at Lane Cove in one of their urban redevelopments. And in 2022, we will be taking a Tesla around Australia charged by printed solar. Where does this leave us in terms of sensing? Well, our focus here now is on being able to develop really low-cost energy monitoring, low-cost sensors to understand the energy that's produced by these systems, and also, of course, irradiance, and for the efficiency of the technology. Where the pathway is taking us is towards energy as a service, being able to create thousands of square meters, in fact, millions of square meters of low-cost energy generation surface. And I'll give just one example that Cardenia Energy is targeting. We currently have over 100 million square meters of industrial and retail roofing in Australia alone that cannot take the weight of conventional solar cells. These conventional solar cells weigh about 20 kilograms per square meter. Printed solar, by contrast, weighs less than 300 grams per square meter. Not only that, conventional solar is not sustainable. There is no current pathway for recycling. Printed solar, on the other hand, is 100% recyclable. We can simply take the materials, wash the inks off, and start again. And with that, I'll stop. Thanks very much.
Thank you very much, Paul. I'd like to introduce now Dr. Tomonori Hu from NSSN to speak.
Thanks, Julian. Hope everyone can hear me. Great to be here. And as Julian mentioned, I am from the New South Wales Smart Sensing Network. I'm the research theme leader for environment and AgTech. But today I want to focus on one particular area for climate change. Is a lot of the work that's been done through the NSSN is in air quality. And we've heard a little bit about that before. But in particular, with all the work I've been doing in air quality pollutants, one that's really jumps out to me is the measurement or the accurate measurement of black carbon. So that's also known as soot, and it's quite often generated from incomplete combustion, for instance, from coal-based power generation, diesel engines, but more importantly for Australia, in bushfires as well. And we all know there's a lot of information out there that it's the second largest contributor to Arctic warming, the first one being carbon dioxide. It spreads really quickly across the world, and given its optical properties, being black, once it gets on the Arctic ice caps and things like that, it's really quite bad news because it absorbs quite a lot of light and heats things up. We've heard today that to make better decisions, we need to be able to measure things more accurately. And I think this is one area that smart sensing could really come in. So being from the NSSN, rather than an inwards and outwards look, we also collaborate with industry and other research organizations and looking at what's out there. And one particular sensor that I want to talk about is called the Maybe sensor, which is a black carbon sensor. It was developed by ANSTO by one of our colleagues called David Cohen, and it's gone so far to be commercialized, and it's being manufactured in New South Wales at the moment. And it has the ability to use optical sensing of 7 wavelengths of light to measure black carbons, but not only that, but also identify the source of it. So there's a little bit of science about in how black carbon is generated, whether it's a diesel engine or whether it's from bushfires. The temperature determines the morphology, and by looking at the optical properties of these black carbon species, you can actually get an idea about where it came from. And I think that's going to be quite important in Australia as the bushfires will continue as we head into the future. We need to know where these are coming from and how much are each contributions from different areas. So at the NSN, we're really keen to work with external partners with our universities. So, this particular technology has been sold over 40 countries, I believe, around the world, and it has incredible accuracy, and yeah, it's just been rolling off the shelves apparently. So, and yeah, just another comment there is there are other black carbon monitoring devices called aethylometers, but the unique thing about this is, well, number one, it's manufactured right here in Australia, but two, it has a lower size, and it's also much more lower cost. And then I think we've also heard today that we need to do things at scale here. One point measurement is good, but we need to actually be able to map where pollutants are coming from. So that's my little chip in for today. I think I want to open up really for a discussion about especially to climate scientists or climate researchers about, we have these devices that are actually manufactured in New South Wales. How do we better make use of that kind of sensor? Where are the data gaps in, for instance, black carbon monitoring? And if we were to roll out a sensor network with these, where are the best places to put them? And I think that's something I'd like to follow up after this meeting.
Thank you very much, Tom. I'd like to now pass the floor to Dr. Nathan Cooper.
Thanks very much, Julian. And in terms of order, this talk is kind of convenient because it jumps off the back of Tom's, as I'm also focused on air quality sensing as well. More specifically on the health impacts from air quality, as we know that is that even though the relationship between air quality and climate change can be complex at times, we know in general that air pollution contributes to climate change, and climate change does impact on many of the sources of air quality, such as bushfires, as mentioned before. And this is really important as air pollution is one of the largest environmental health risks globally, responsible for an estimated 4.2 million deaths across the world. So for this reason, and we've seen the effects of this obviously in Australia with the 2019-2020 Black Summer bushfires, which are predicted to grow in frequency and intensity as our climate changes over time. So for this reason, it is important that we do have appropriate sensing systems to accurately measure air quality in Australia, and also, especially in the environments that people spend the most time in. And currently in Australia, our air pollution networking systems use a lot of traditional methods such as gravimetric methods, which are very accurate, but they're incredibly expensive, they're very bulky, and they require a lot of maintenance. And consequently, most monitoring is very sparse and is generally conducted only in urban background areas, which aren't really representative of the many exposures that people go through on the day-to-day, such as when they're near traffic, going to work, or even just in their homes. And most importantly, there's no network monitoring for indoor environments, despite the fact that Australians spend approximately 90% of their time indoors, again, whether at work, home, or school. And as we go into indoor environments to protect ourselves from outdoor sources of air pollution, and as climate change threatens to exacerbate other environmental hazards such as heat waves, for example, having healthy air quality and having healthy indoor spaces is going to become increasingly important as we go into the future. So while traditional air quality monitoring methods aren't really equipped for this task, fortunately, in the last 10 or so years, there has been the development of low-cost sensor systems for air quality. And these allow for a greater range of environments to be monitored at an increased spatial resolution and a temporal resolution, including indoors. Now, some of this is a trade-off in accuracy compared to traditional monitoring methods. They do require a greater degree of pre-deployment sort of work, where we set up low-cost numbers next to government sensors to test how well they compare with reference measurements. But once that work is done, they do offer an adequate level of measurement of accuracy of air quality in indoor and in outdoor environments. And they're also particularly good for informing air quality, what characteristics of indoor environments are useful, protective, or what actually increases exposure to outdoor air pollutions that infiltrate indoors. And so for these reasons, the research team that I'm part of, which is actually led by Associate Professor Donna Green at UNSW, have been using these technologies to conduct the Clean Air Schools project, which aims to measure air quality inside classrooms and in schools in general, to measure children's exposure to air pollution, and also to understand the characteristics of these environments that affect children's exposure to air pollution, so that we can develop appropriate actions, whether on the ground actions that can be taken by schools, or policy actions that can be taken by state governments, for example, to protect children from air pollution. And our analyses don't just look at standard air pollutants such as particulate matter and nitrogen dioxide. We also look at these measurements in relation to carbon dioxide levels indoors, which are a proxy for ventilation rates, as well as meteorological factors such as temperature and relative humidity. And these are really important to kind of measure in conjunction with each other, because Many of the current suggested measures for reducing air pollution exposure indoors may impact these other factors. In particular, in light of COVID, we know that improving ventilation is important for reducing disease transmission, but during bushfire events, improving ventilation can actually increase your exposure. So we are trying to analyse these factors to understand the benefits and also what actions can potentially improve both. And this is really important for some of the sustainable development goals, and particularly for developing sustainable cities and communities by providing access to safe housing and services that are not exposed to hazardous levels of air pollution, and also to creating for Sustainable Development Goal 13, climate action, by creating resilient and adaptive communities and adaptive capacity in those communities as well. So yeah, we're really excited about this research, and we hope that it can be used in the future to fully realise the benefits of safe indoor air and air quality in general in changing climate. Thanks.
Thanks very much, Nathan. I'd like to now welcome Professor Corrine Caillaud from the University of Sydney.
Thank you very much, Julian. And before started, I would like to acknowledge the custodianship of traditional owner of the land on which I'm seated today, who are the Bidjigal and the Gadigal from this part of Sydney, and acknowledge their leaders, past, present, and future. So the conversation I wanted to bring into this forum today is linked to one of the big research projects I'm involved in at the moment. So I'm a professor at the University of Sydney. I'm in the Faculty of Medicine and Health. And really my research is around digital health and sensors and smart sensing to promote self-monitoring and improving human health. But the project I'm involved at the moment relates to agriculture and family farming, and the connection between family farming or farming practices and health in Australia, but also more widely in the Indo-Pacific region. And this is something where I think Australia not only may have the capacity to provide solutions, but a huge opportunity for leadership as well, and to try to think how smart sensing could really be part of the solutions we envisage. So I guess the point I'm starting with is the fact that agriculture has a huge impact on climate change. We know that producing and transporting food has a huge impact in terms of producing greenhouse gas in the world. And Australia is positioned as a large producer of these gases in terms of either producing food or transporting food. So we know that one of the solutions may be, amongst others, that there's the capacity to produce food more locally and to consume that food more locally. So the challenge here is how can we envisage that smart sensing could help producing food locally, but as well support farmers working in small size or medium size farms to engage in sustainable practices that will have an impact on soil quality, water use, and land quality as well. So really the context is that we know that, for example, transporting food has a huge impact on emission of greenhouse gas, but we know as well that for many communities in Australia and in the Pacific region, having lots of food coming in and food that is sometimes quite usually westernized is not the best outcome that this is going to have on their health. And so there's a really positive and lots of rationale in trying to understand how small size family farming can be expanded and can be sustainable in the region. So the challenge is to actually produce some affordable, low-cost sensing that would help farmers to better monitor the practices in the farm to increase the producibility, to potentially limit occurrence of pests, and to have a better use of potential chemicals that they may be using to increase productivity. I think we could as well have a better understanding of what's happening locally with some sensors on the ground. And again, and in alignment in what others have said in this forum, smart sensing and connecting that information and sending that information so it could be analyzed and potentially develop predicting models that would be relevant locally for farmers in the region. So this is the challenge we want to make. This is how smart sensing could be made affordable and made usable for farmers in all of the Australian and Indo-Pacific region in such a way that we can improve local farming, local practices, and as well to have a better, embedding of planet health and human health in that sector. Thank you.
Thank you very much, Corrine. I'd now like to welcome Professor Salah Zakaria, also from the University of Sydney.
Thank you, Julian. And just going off what Corrine was saying about looking at sensing and smallholder farmers in agriculture. So my background's in field robotics. This is all about building outdoor machines that have to operate 24/7 in all weather conditions and very unstructured environments. And the whole idea of the robots is to be able to carry sensors and also simultaneously act on the environment based on the information that comes from those sensors. So that's really where the focus of the field robots are. Over the last 15 years, my colleagues and I have been focusing on the use of field robotics in agriculture and environmental monitoring, and the two work with each other, obviously hand in hand. And our focus has been on 4 areas, which I think are relevant to this particular roundtable. One is on building, for want of a better term, green robots. So these are solar electric robots where you're trying to optimize the weight, power, as well as the algorithms, the control algorithms on board to utilize as least energy as possible while out there in the field. And being solar electric, the idea being able to regenerate as well, use less and less batteries as time goes on, and use more and more of the solar elements in those design principles. The platform then carries a number of different sensors, and in an agriculture environment, we've toyed with LiDAR, hyperspectral, infrared, thermal, color cameras, etc. And then you focus a lot on data fusion and how you bring all that information together to represent something about the environment or the plants that you're seeing or the animals that you're tracking. Then on those robotic platforms, you then focus on machine learning techniques and AI techniques, but as roboticists, our focus is on real-time AI. So we want to take in that data while the platform's moving and in real time, convert that information into knowledge. And that's important in order for the robot to then act upon the environment. And that's when you start to add precision tools, intelligent tools of some form, whether it's directed spraying, so you minimize the amount of chemicals that are used in the environment, or mechanical tools that interact with the environment in some form. So when you couple those things together, so a green robot, data fusion techniques, real-time AI, and then intelligent tools, it goes back to what Ben was comment that he made right at the beginning, which if you can't manage what you don't measure. And in our case, what we're trying to do is shrink the temporal gap between the measurement and the management process. So the robots are on farm or out in the environment, and they're sensing the environment, turning that into knowledge, and then acting upon that data in real time. And that's really what our focus is on. And in the agriculture, that's where we've seen some of the greatest benefits, and in particular why the influence that climate change is having on food production, as well as what agriculture contributes to that process. So if you look at it in terms of what climate change is how it's impacting agriculture. So going off what Corrine was mentioning before, we've had some of our robots in Indonesia, Fiji, and Samoa, as well as around Australia. We build these platforms to be really small and work on smallholder farms. And when you see what happens with climate change, you see the impact that very rapid weather events happen and how that affects yield, for example, but also the introduction of new pests and diseases that they've never seen before. And so being able to act upon that information in real time is important, because the way they grow food is they try and hedge their bets. They grow 6 or 7 different types of crop varieties, hoping that 2, 3 of them will actually make it through to the other end. And there's waste in that process, both in terms of chemicals used, but also land. There's soil degradation that happens in that process, and that has an impact as well around climate change. So these are the things that we focus on, and our goal is to be able to help smallholder farmers around the world and food production in general by placing these platforms out on farms that not only support farmer knowledge and what they need to do next, but also have a very small environmental footprint themselves. So the effect that they have on the environment, it needs to be small as well. And one of the key things that we've learned when it comes to sensors, and now being very specific, is the use of off-the-shelf sensors as much as possible, especially in smallholder applications. So the use of, for example, smartphones now, which have enough sensing and computational capability to be able to run a lot of our real-time algorithms, and they're ubiquitous. And we're noticing now how more and more startups are using different types of sensor plugins for those smartphones. And I think that's an important element that we can look at as well as down the track. Thank you.
Thank you very much, Salah. On a related theme, I'd now like to introduce Professor Sarath Kodugoda from the University of Technology, Sydney. Thanks.
Thanks, Julian. This is a great segue from Salah's talk to talk about different applications of robotics in different areas. So my background is in sensors and specifically using robots to take those sensors into different areas to make informed decisions and measurements. So what I'm, and also as previously Michelle mentioned about urban areas, how important the urban areas that can play in this global climate change aspects. So I'll be focusing on infrastructures and how can the sensors be and the robotic systems could be used in infrastructure to monitor the conditions of the infrastructures and make informed decisions about them. So I'm pretty sure you are aware of the cities that we are living in, and under those cities, there are many networks. One of them is a water network. So those, whenever you open the tap, we like to have water in our taps. So the waters are normally transported through metallic pipes, and those are in most of the cities, those are around 80, 90 years old. And when with the time, it started corroding and aging. So there are no sensors out there to figure out what is the condition of those pipes. So one way to monitor is to have the sensors built, at the same time take those sensors through the pipe, through robotics means. So our team, our colleagues at UTS has been working with Sydney Water in developing several generations of robots with sensors to measure the remaining thickness of those pipe walls by inserting through a small insertion. So in this way, you don't have to disrupt the traffic. You don't have to make people inconvenient. So it is doing the job while the normal day-to-day work is happening in the city. So another aspect is, I'm pretty sure you can appreciate that the sewer network. So Sydney alone has around, I think, more than 20,000 kilometers of sewers. The difference with water is that these networks mostly are not metallic. So those pipes and tunnels can be in concrete, mostly concrete. So the corrosion or the deterioration of those different pipes are different. And you can't use the same sensing technologies that you have used in the water pipes, which are metallic, in order to assess the corrosion in the concrete pipe. So again, my team here at UTS developed robotic systems with sensors in order to measure the corrosion and intact concrete remaining to reinforcement bars, and measuring the three-dimensional structure inside the pipes so that the water utilities can make informed decisions about it. So the third example that I'm going to give you is about other structures. For example, if you look at the harbor bridge, I'm pretty, you're aware that need continuous inspections, condition assessments to make sure that that is safe for users. So one of the problems is the corrosion. So it is painted, and how could we identify and repair those corrosions before they do anything to do with the structural damages? So in this respect, again, our colleagues at UTS has developed robotic systems which can take automatically measurements about the structure as well as corrosion patches and do the paint removal in a robotics way. This will help, on the other hand, for people, because most of those paints are lead-based. So we don't want to expose anybody to lead-based paint. And the other thing is the grid blasting machine itself has a reasonably high force, and using longer term can affect your back. Therefore, obvious application is that. And also another team at UTS, I'm aware that using large number of sensors mounted in the harbor bridge in order to measure, for example, vibration data, and use them in the machine learning algorithms in order to predict deteriorations and different aspects. So sensors wise, there could be infrastructure mounted, which can give different information. And also there could be sensors which you don't need that often. And maybe those sensors cannot survive in some environments. For example, the sewer example, it is very hard to survive sensors in a sewer environment due to the things that we flush and due to the acidic nature. So in those cases, how to have the sensors built, at the same time, how to take that sensors to the required place at whatever the intervals that you would like, that can be done through robotics and technologies. So it could be a combination of different aspects, technological developments that can be used in order to build new infrastructures, maintain them, or decommission in a sustainable way. Because the cities are very important part of our human life, and the cities, as I think Michelle mentioned, estimation is that by 2050, 2/3 of the world population will be living in urban areas. So we need to facilitate that. Thank you very much.
Thank you very much, Sarath. I'd now like to turn to Professor Peter Ralph, also from the University of Technology, Sydney.
Thank you. So I'm going to give you the punchline first. So I'm going to focus on climate change. I want to talk about cheap handheld carbon sensors, and I want to link it to verifiable carbon trading. So I'll take John's lead and tell you what I do know and what I don't know. So for the past 10 years, I've worked on developing the blue carbon assessment and monitoring manual. This is a document that goes to the UNFCCC. So this is how do you measure stocks and fluxes of carbon in nature-based environments? And this is going to be a critical part going forward in COP26 and the future of essentially how we manage the planet. So I know a lot about eddy covariance systems, soil carbon coring, aquatic carbon flux measurements, remote sensing of boundaries. This is all the old stuff that we've done over the past. I have to excuse my cat for Zoom bombing me. This is the kind of stuff we've been doing for 20 years, and it's not going to be fit for purpose for the future. So we are going to have to rely on nature-based carbon sinks, and the technologies that we've used in the past are inappropriate. I loved what Subhas was talking about with his low-tech, cheap, deployable sensors, and this is what I think the future is. So I know what we've done in the past. I'd really love to work with teams to develop something that's needed for the future. So for us to get carbon trading working, we have to be able to verify where the carbon's come from and where it's gone. Now, using an oven to combust soil carbon is a pretty damn low-tech way of doing it. And what I need to have is I need to have farmers that can go out on their property, grab a handheld sensor, stick it in the ground and say, I've got 5 kilograms of carbon in this hectare. They need to go across and do some biochar, spread some biochar, and understand how much carbon's gone into their soil. As a plant physiologist, I've read around, I'm a little bit excited by shortwave NIR sensors, and you're able to get potassium, nitrogen, phosphorus, and soil moisture, but to my limited knowledge, you can't get carbon. We need to have a system where we can have a handheld deployable carbon sensor that these end users can verify how much their carbon is being stored. So this comes back to the flux and the stocks that you've got to be able to measure. So whether it's in forestry, and forestry, we've got some pretty low-tech systems, measure the girth at breast height, use remote sensing, you can track your carbon that way. But when it comes to soil carbon and my area of research, which is algal-based carbon measurements and carbon storage, this is getting really difficult. So I see into the future that we're going to have carbon capture and manufacturing, not carbon capture and storage. So we will be able to capture carbon and turn it into bioplastics, turn it into building products. These are going to be sources that are going to hopefully attract a carbon credit. And therefore, we're going to have to verify where that carbon is over time. Now, if you can't do that, it's not going to get carbon credits. The carbon border adjustment mechanism is something that's going to dramatically impact on Australian manufacturing. If we cannot verify where our carbon's gone and how we're decarbonising our production systems, we're not going to be able to trade. So I think the opportunities here for this group, if there's technology available that I'm not aware of, that there's some clever people in the group, I'd be really excited to work with them, because I think the circular economy is going to be something that the governments are going to be investing in. And if the circular economy isn't using carbon as a commodity that we're trading, we've got a sewage treatment plant, we've got nitrogen, phosphorus coming down, we've got an anaerobic digester making biogas, the methane goes somewhere, but the CO2 has to go somewhere else. We track that carbon, put it into biomass, and then we can trade that and say that that carbon's locked up. This requires some very, very cutting edge sensor technology. It requires the Internet of Things. It's Industry 4.0. It's the future. And I hope there's opportunities amongst this group to be able to develop that. So I look forward to the discussion, and I like telling everyone what I don't know.
Fantastic. Thank you very much, Peter. I'd like to now turn to Professor Paul Hurley from Western Sydney University.
Okay, thank you very much, Julian. I hope you can hear me. So today, I'd like to talk about the impact of algorithms in regarding to sensing and their impact on climate change. There are two things that we can do to help regarding mitigate climate change. One, of course, is improving the accuracy with which we sense, so we're able to understand our environment better around us. And the other thing that's also a crucial thing and very much linked is mitigation, which is reducing the footprint we have on climate change. Because even when we have low-powered sensors, we then actually farm a lot of it out in the cloud, and computing power is becoming an even more significant cost and burden on our resources, and is of basically important for us to reduce this down. We don't want to be doing something like a cryptocurrency which uses an insane amount of resources just to do something that's essentially, in some senses, useless. So there's been discussion about the fact of within climate change, whether we need to, when we can fight climate change. Typically, that's a very common theme. We're going to fight it, we're going to beat it. But to a large extent, we need to adapt it because climate change is coming. It's a question of how much is going to come, sadly. And therefore, of course, the sensors that we're going to use are very critical in that. Within this scope, where do algorithms play a role? So one of them is the interaction between hardware. Sometimes we can design sensors for the hardware and then afterwards put on the algorithm to try and do the best we can. But if we want to reduce the amount of footprint that these sensors have and to increase the information that we have in them, we need to design them together and interact them. And one thing that we can use very much in this particular case is nature is extremely efficient at sensing, and we can learn an awful lot from that. And in that sense, we want to be biologically inspired and to bring on notions, for example, of neuromorphic computing, where we do things in an efficient manner, but maximize the amount of information we do. So one example of nature being particularly efficient in that case would be, for example, we adapt what we actually focus on. So when we look at the screen, and I'm looking unfortunately over at the wrong camera, so my hand is turning to the side, but when we look at an audience, we adapt what information we absorb, and we ignore, very importantly, the information that we don't want around us. I achieve that by having the blur on the screen, so you don't see that I'm actually sharing an office with somebody else too clearly, at least. But what we do is we adapt and we efficiently acquire the information that we're interested in at the expense of what we're not interested in. And that's because we know something about our environment. And knowing something about our environment leads us then to be able to choose how we do that sensing. And this is going to be a crucial factor in reducing the amount of footprint that we have. On a concrete example of that, we're developing algorithms on a phased array. So essentially a sequence of sensors for astronomy, and it can also be for other applications as well, but let's say it's on the astronomy case. And typically the observation times that we have for various reasons in astronomy are extremely long in duration. It can be 8 hours that we're doing sensing in order to acquire the information that's out there, because the signal is pretty weak. So the noise levels are quite significant. So you need to acquire for a long period of time. But actually, this is a very static form of sensing. What we're doing is we're just observing. So it's a hardware that's basically just observing in a fixed manner, where we're not changing very much. But after even a few seconds, we have a rough idea of what we're actually trying to observe. So it seems kind of a bit of a waste of resources, and indeed it turns out to be so, to just simply keep observing, and then at the end, then try to process the information that's there. And so what we're doing is we're learning what's out there. We know that this is mostly part of like white space. We don't need to concentrate so much. So we change our focus the same way I was mentioning that the eye changes its focus. We focus on that part at the expense of not learning too much more about what we essentially know are uninteresting objects in that particular part of the sky, and taking that inspiration for that. And with that, I'm coming to the end of my 5 minutes. Thank you.
Thank you very much, Paul. Finally, I'd like to welcome Associate Professor Brendan Choat from Western Sydney University.
Hi, thanks very much for inviting me. I work at Hawkesbury Institute for the Environment at Western Sydney University. And understanding and adapting to the impacts of climate change on natural ecosystems and agriculture is one of the central missions of our institute. A bit about me, I'm a plant physiologist. I'm mainly focused on how plant stress affects natural ecosystems and horticultural production. And much of this is based on how climate change is pushing these systems. What are the risks and how do we adapt to them? So I spent a lot of time over the course of my career making measurements of plant stress, particularly water stress and heat stress. These measurements are very important in determining a whole bunch of things, like when trees will die from drought stress, when plants shut down photosynthesis, and when you need to switch irrigation on and off to keep plants at a desired set point. So it's a certainty at this point that extreme drought and heat events are going to become more frequent in Australia, and they're going to be exacerbated by climate change. And this is a real threat to our environment and our quality of life, and it's something that we have to address. Measurements of plant water stress are traditionally made by manual methods, which are very laborious. We use an instrument called a pressure bomb, which we have to lug around. They're particularly bad when these measurements have to be made prior to dawn to evaluate equilibrium moisture stress. So this is something that I'm hoping that we can shield future students in this field from. So developing sensors that measure plant moisture stress continuously has been challenging in terms of developing sensors that are robust, accurate, and cost-effective. There's lots of exciting developments in this area, but it's a big challenge and it needs more investment. As Suvesh noted earlier, making these sensors cheaply enough is really essential to being able to roll them out at scale. And that balance between making them cheap and making them still robust and accurate is really what we have to attack. Of course, there are lots of useful applications for these sensors. I'm really interested in ecological monitoring and precision irrigation applications, but there are many others that we've been touching on this morning: urban green spaces, as Michelle mentioned, bushfire risk, as Marta mentioned, and many more. Ecosystem monitoring along the lines of the TERN network is really essential in my view, and we don't currently monitor plant stress directly. And so we can use remote sensing techniques to get at plant stress and plant productivity, carbon storage at higher scales, but there's always concerns about if you don't have good ground validation. So being able to make sensors cheaply and roll them out at a scale that's useful, that's the problem, and that's what we really need to do. It'd be absolutely amazing to have these sensors rolled out across TERN sites and other monitoring permanent plot networks around Australia, and would really help in terms of being able to assess the impacts of climate change, also in ecological forecasting, because ecological forecasters need real-time data at high temporal scales to get continuous improvements in their forecasts. Precision irrigation is another important application that I'm interested in. There are a lot of systems available at the moment. Most of them use soil moisture sensors, but these are often not really representative of the moisture in the root zone of the plant or the actual stress that the plant's under. So having sensors mounted on the plants is going to be much better. There are systems that are commercially available at the moment, but they tend to be quite expensive, running at $2,000 to $3,000 a sensor. That's not really tenable for a rollout at the scale that we need. So we've been developing more cost-effective sensors with our colleagues at the University of Tasmania. These are based on very cheap components and cameras that measure the expansion and contraction of petioles and stems in the plant, and they can be produced fairly cheaply. And there are some success stories already emerging. When the sensors were trialed on pyrethrum crops, they showed that previously they'd been over-irrigating these crops, and when they reduced irrigation dramatically, it also helped limit fungal pathogens in the soil. So these are the kind of advantages that we can gain with these sensors. I'm coming to the end here. I just wanted to say, as the last speaker today, that it's been really inspiring seeing all of these talks, and I think there's so much potential for collaboration between the researchers. I'm already collaborating with some people, but I look forward to the further conversation, and that is my time. Thank you very much.
Thank you very much, Brendan. I'll now pass over to Ben to chair the next part of the proceedings.
Thanks, Julian. Wow, this is going to be fun. That was fantastic. I've got pages and pages and pages of notes. And it's fair to say we're going to have to unpack this. So let's have a bit of a discussion. But look, tremendous capability, isn't there? And, I learned so much just in that hour. And let's hope that there are indeed some opportunities for new partnerships, collaborations that emerge from this discussion and the conversations that follow. So this is open. I've got some high-level comments and then some specific comments. I mean, clearly, we've covered a lot of ground, and I thought I could actually rush through those 15 presentations, but actually that probably will take 5 to 10 minutes. Lots of thought-provoking perspectives. And I might just dive in and see if this sort of sets us in a direction for a conversation. This is a bit random, but I'd love to go back to Peter's presentation on measuring carbon. The notion that if we can do that more ubiquitously, low cost, what is the challenge there? And if we can build that sensor and have them everywhere, are you hinting at that measure and effector that is now going to change our behavior? Is that something that you can foreshadow?
I was going to, well, I suppose I'll quickly jump in. The hope that I had was that these sensors would be linked to allow direct carbon trading. So if a farmer cannot demonstrate their carbon content has gone up in a pasture due to an action that they've done, they're not going to get that credit. So this is going to be a way that we can help the government to get new jobs building the sensors, but also get carbon farmers as a new industry. And I think the opportunities for Australia are massive, but until we've got those sensors, we can't trade and we can't take those carbon credits from around the globe. And whether the carbon's in the soil, whether it's in biochar, or it's in a bit of plastic, you know, they're all the places that we need to be able to store it. And I think it's just a sensing question. I don't think there's a problem with the data. I think blockchain's going to look after that. I think there's no problem with the trading systems, but it's, can we get nature-based stores into the market?
Is the carbon dioxide measure itself a mature technology? Is there a grand challenge there? I mean, what level, where is that up to?
Look, I'd cast it back to the broader group because in preparation for this meeting, I had a look through the sensors that I could find, and the best I could find was shortwave and NIR. And I thought it looked close. And I think there's a lot of smart people on this call. And I'd love to be told, Peter, you're an idiot. NIR is already available and you just need to buy this sensor, but I cannot find it. And I don't care what the technology is. I think it just needs, and we don't need precision. And I think this is part of the discussion for trading systems. We need to be able to measure a defendable proxy as opposed to a scientifically publishable, there is this many grams of carbon stored. So I think this is where there's a bit of pragmatism amongst the science and engineers that we need to be able to think for a trading system as opposed to a plant monitoring system. And I'm absolutely not suggesting this is a plant health monitoring system. This is a discrete, where is that carbon? And prove to me that it's still there 10 years down the track.
Yeah, does anyone want to comment on that? Is there an expert who wants to give a perspective? I note that someone's put into the chat an example of a carbon dioxide meter.
Not carbon dioxide. Carbon dioxide, we can do that in a heartbeat. It's right. Carbon in the soil.
Yes.
And carbon in the plastic. So yeah, CO2 sensors, we monitor that. And that's where the industrialization works perfectly, because we can measure carbon going into biomass and we can measure it going out. So CO2 per se is fine, it's carbon. That's the problem.
Brilliant. Look, I'm just going to keep asking questions, but I think this is a conversation everyone's part of, so feel free to chip in. Corrine, you didn't talk explicitly about global disease burden, but as you think about from a health perspective, can you give us a perspective on global disease burden and how that's captured in these conversations, and any perspectives on how sensors play a role in that?
Yeah, it's an interesting point, Ben. Well, you know, I think we know what we know now, and what's happening in different, I mean, globally, is the impact of processed food and Western food on obesity and cardiovascular disease. So there's there may be a direct relationship into empowering populations and communities to produce food locally, while managing soil, managing pests and yield. So we can, at the same time, potentially have an impact on the emission of greenhouse gas and health. I found very interesting as well, the possibility to use different types of sensors. I mean, maybe there's a combination because we talked about, satellite images that could be used, but I think there's potentially something very interesting in empowering people as well to provide some data. And I thought that the use of smartphone to provide some kind of information on local images is very interesting as well. To push it a little bit further, maybe we could even have, sounds and a bit of people's narrative around what's happening. It's a bit more complicated. It's different types of sensors, but it's trying to capture nature and human experiences at the same time.
All right. I'm going to open the floor because I wanted to really encourage questions. I mean, I could talk, but I know we're all struggling to absorb all of that fascinating perspective, but it really is open for questions in any particular direction. I mean, clearly there's an emerging, the theme of sensors that are cheap, robust and accurate, handheld deployable carbon sensors, shrinking the temporal gap between measurement and the acting, I think is a lovely theme that we heard from Sala, using off-the-shelf smart sensors, as Sala and Corrine just mentioned. We heard the importance of indoor air quality. We heard very nicely stated, not only does the pollution impact on climate, but climate impacts on air pollution and health. We saw a beautiful example of energy monitoring from Paul. We heard from Tom talk about black carbon and an amazing sovereign capability that's being commercialized. I mean, I can go on and on, lots of themes there. I can see that Peter's got his hand up. So Peter, over to you, back to you.
I just wanted to be polite and do the way that you're suggesting. I want to ask a question about Tom and Paul. I'll open the first one up with Paul. I wonder if Paul could explain some more of the opportunities for the semiconducting polymers apart from photovoltaics and energy capture. Equally for Tom, he's got a black carbon sensor which is based on optics. Has he got my solution? He said that it's using 7 wavelengths and it's sensing black carbon, so it's particles. Is it the carbon molecule or is it just the shape of a black thing that he's measuring? So 2 questions for 2 of the presenters.
All right, well, shall I kick off, Peter? So in terms of our opportunities around semiconducting polymers, I think one of those is really around, we've focused on development of biosensors. So we've developed sensors, for example, for biomolecules, in particular glucose, which has also been commercialized, and we're now in the process of building a manufacturing factory for that here in Newcastle. That's just been funded through the MMI program. So I think there's an enormous opportunity for us to think about sensors that we can print at extraordinarily low cost and at massive scale. I mean, to give you an example, we print around about 1 kilometer of sensors at a time. It's 300 millimeters wide. I mean, the scales are just vast, even at our pilot scale, let alone manufacturing scale. And so I'm thinking, as I'm listening to all these talks, where can I see the opportunities, for example, to be able to answer the questions that you're asking quite reasonably, Peter, which is, in particular, as we move towards a net zero plan, of course, that means you have to count. Otherwise, people will cheat. And so that's what you're outlining is absolutely critical. Being able to accurately count and verify that what people say is happening in terms of stored carbon, etc., is in fact the case. And so, yes, I'd be interested to think more on that topic, especially if you see potential there and how you would see that working. But I'll stop talking there, sorry.
I was going to say exactly, you've got biosensors doing glucose, guess what, that's carbon. So as a photosynthesis guy, I'm sure that there's not a huge amount of steps to get to a simple carbon sensor. So awesome, let's chat, because it is cheap. Your technology is cheap, and I thought you might have gone beyond the photovoltaics. So the biosensors is perfect.
Great, Tom.
Yep, I'll jump in and answer that question. So thanks, Peter. So I guess maybe I'll start by saying it's not my sensor, it's developed by another person. I'm not claiming anyone's work, but it is a very impressive piece of work. The answer, the question was whether it worked for you. These devices work on depositing, I guess aerosols onto a disk. So it's very selective. So you've already got the aerosols, and then within all sorts of other particles, you shine different light visible wavelengths through. I think one of them is actually near IR, so it's more close to your near IR solution. And then for the physicists in the room, you do simple kind of absorption via Lambert's law, and you work out the concentration based on how much light gets through at different colors. So I would say maybe it's a bit more closer to your near IR. So maybe not as simple as you'd like, but I mean, there are soil reflectance measurements as well, using different colors, so infrared and even mid-infrared light, which I know a little bit about. I guess I'd like to know more about how you want to use it, because if you've got mixtures of soils and other things in there, it does quite make it difficult. But happy to chat with you afterwards and figure out what the solution needs to look like.
Yeah, the fact that you've got a range of different wavelengths kind of encourages me, because it's not just an optical signature. So soils are not soils, and there's all kinds of different parts. But is there a technique that can wavelength dependent identify the carbon as opposed to the silica, the clays, all the other compounds that would give a different signature? So it equally, imagine a smartphone. A farmer gets a smartphone, puts a smear of soil on their lens, presses a button, and they've got a proxy of the amount of carbon in that soil profile. How awesome.
Yeah, let's chat more maybe after this. You'll find startups out there who can scan fruit and say they've got all the molecules. I doubt that level, but I think if you selectively say under these settings, we can do.
That's a great follow-up.
Yeah.
Good one.
Cool.
Again, open for anyone to chip in. I can steer the conversation in all sorts of directions. I'm intrigued by Paul Hurley's perspective on, which I think is really talking about edge computing, the narrative. I think you're saying on the one hand, there's a lot of energy involved in the computation, and that neuromorphic sensors, for example, there's a lot of information that isn't processed because you get to see what you want to see. Do you have a sense of what is the energy saving in a neuromorphic computing architecture for large sensing networks? I mean, have you run through the numbers? Can you make that concrete?
No, that would be a good thing to do. I don't have any concrete numbers for how much this would reduce, but of course the idea is then, and it's very hard to gauge as well, because then once you actually use those sensors, it depends what you're trying to measure, how much you're going to get out of them. So it's really, really hard to gauge it. And we concentrate mostly on increasing dynamic range to see what we actually can acquire from them. But that has the effect that we don't actually need as much power as we would normally need at that sensing point. As long as we don't then, and as you just mentioned, we just basically don't push the problem onto the cloud computation and have an extremely hard inverse problem to solve.
Yes, there was a narrative 10 years ago. I had myself come from an optical communications background, and at some point there was a narrative that the internet, routers in particular, consume 4% of the world's energy consumption, and it's growing, and it was growing faster than the airline industry. And at some point it was predicted to exceed for Japan, the entire energy budget. Now, that didn't happen for various reasons, partly because of innovation, partly because the networks were reimagined. But it really does make the point that there is energy consumed by the internet, and there's energy even consumed by sensors. So there's even an interesting conversation around, if we really do create these ubiquitous low-cost sensors and they're everywhere, are we actually creating a burden on the environment? Anyway, that's just a point. But open up for more perspectives, more discussions. Even going back to the earlier perspective, John Close, Mark Vermeer, and you, the sort of satellite gravitational perspective was fascinating. Martin, we've heard, I think, your narrative for the last few years, and just to see how quickly that is moving forward. And you know, there's been such progress in the last few years in that space, no pun intended. So we can open for questions. I'm just looking at the chat. So Julian has said a few speakers have touched on the need to validate fuse big picture data, e.g. from remote sensing, with very local on the ground data. Does anyone want to talk in a little more detail on the needs and where it could have the greatest impact?
Perhaps I can make a comment on that. So from the bushfire perspective, the need is that they offer different ground resolutions and different time resolutions. So as I quickly mentioned, in terms of active fire detection, the closest the sensors are to the ground, the higher the chances are to detect a fire as soon as it ignites. But of course, the lower the coverage of those sensors, unless we put a very cheap sensor network that can be located all across Australia. So that's why those ground sensors might only be possible to be located in strategic places to complement gaps in other sensors that are in towers, for example, that those sensors in towers have blind points, and complementing the capability from the satellites, that the satellites have that eye in the sky that can see across Australia, but they don't have the ground resolution that is needed for early fire detection. And also they can have different sensors themselves. From on ground, you can be monitoring the chemical composition of the fire and the smoke. You cannot do that from the satellites. Well,
good one. Again, looking to the panel for other questions, thoughts, thought bubbles. Yes, Brendan.
Yeah, I was just actually going to touch on the question that Julian put forward and that Marta was discussing. Just, you know, as an example of something where we need to have a bit more capacity for ground truthing, we have a project looking at tree dieback and, you know, the death of trees in New South Wales. And after you have a large, you know, kind of regional scale event like a big drought, like we've had recently, you have lots of trees dying, and the ability of satellite-based platforms to tell you whether the trees have died is often a bit limited, because you get, after the trees died, you have the canopy falling away, but then you might have ground cover coming up under that. You know, you have grasses and weeds that come back very rapidly, and that will obscure that signal. You know, if you have sensors based on the plants, that's obviously going to tell you whether the tree has died and is not coming back. The trick is just, you know, how you balance those scales, because you can only roll out a certain number of sensors. The cheaper they are, the more you can roll out. There's also, you know, a bunch of labor and maintenance costs associated with that. But as Marta said, you know, you're not going to get the coverage that you do with remote sensing. But you need, you can have training of those systems, you know, so that's where the real benefit is. If you have enough of those sensors rolled out, then you can improve the accuracy of what you're trying to predict with those.
Yeah, good one, good one.
Ben, there's probably I can say a few comments here that would be relevant to this question. So as I mentioned in my 5 minutes, the gravity has been very, very successful. Measurements of gravity have been very successful in elucidating groundwater movement from satellite-based measurements, or at least what they're good at doing is they can see the effect of groundwater movement. But one of the major questions is you don't know how high or low, how much the water has moved, because you have to know soil properties. You have to know the storativity of the soil and so on. The project we're involved with is precisely of this nature, where we're combining, we're studying catchment systems where there are boreholes. So we know the idea is that we will know what ground truth is. So the borehole measurements will tell us what the water is actually doing. And then we get out there with our gravitational sensors and we make gravity measurements. So we make a grid of measurements. Then we mathematically invert that in collaboration with our colleagues at the University of Sydney, and we compare what we learned from those gravitational measurements in terms of water movement with what ground truth was. So it's a whole procedure in trying to investigate and bootstrap gravitational measurements and gravitation and inversion of those signals to elucidate what the water is doing. But there's a lot of open questions in there about validating the technique, validating the model, combining it with satellite data and so on. And one last very quick comment here. I think so we're in the opposite regime to many people. So many people here are speaking the very important question of cheap, so low cost sensors rolled out at scale. The sensing modality we're talking about is the opposite. It's not a cheap sensor. It's not going to go out on scale. And so it has to be a problem where we need to address problems where it is really this expensive sensor brings attributes that other sensors simply can't get. And so this is where the stability, the extreme stability and the inherent accuracy of these sensors is probably important, but ground truthing them and validating and developing the techniques, including the mathematical inversion and the connection to satellite data, is quite critical.
Thanks, John. I have questions, but I note Salah's hand is up, so I'll go to Salah and might come back to you with the follow-up if we've got time. Salah.
Just quickly, maybe beyond just sensors as a data fusion approach. So we have done work before where you're fusing satellite data with ground-based data, where the ground-based data might give you slightly different spectral responses at a different resolution, but you can work out machine learning techniques that correlate that information to the satellite data at that particular point in time, which then is used to then predict what the ground data would look like at other parts that the satellite information is collected information from. So the ability to be able to correlate the ground data with the satellite data is important, and there are techniques there. And probably something to put into this context as well, I guess, in the context of this roundtable, is what happens below the ground. So we haven't talked about how below ground information with above ground information should be correlated, because there's so much that goes on. And we have slightly touched on with carbon, for example, but anything from like microbes and root mass and distribution has an important influence on climate. So if you can bring that type of information, fuse it with what's happening above ground, then there's better holistic models, I think, that can help us go forward.
Yeah, interesting. And by below ground, I guess John Close is not going to be able to help with his quantum sensor on some of those. Interesting. John, Salah's point's excellent. So, John, what's the timescale for getting one of your sensors into space?
Into space. I think that's going to be a few years away, and it'll probably be. I would like Australia to have an involvement in that, Ben, and we're talking with a variety of groups around Australia. It's highly unlikely that Australia will field an entire quantum sensor that would be space-based. We would be a part of a collaboration with Europeans and the Americans. Developing some of the technology is probably the way forward. But in the shorter term, it's the terrestrial measurements that I think we can make an impact, And those sensors, Ben, are probably, so we've developed field deployable size, weight, and power sensors in our lab, but still a lot of work to do to ruggedize them and make them appropriate for true field deployment. As you know, Ben, rapidly growing quantum industry in this area, and I'm pretty optimistic that we'll see these devices. At least, I think we're going to see these devices in field deployed applications certainly within 5, probably within 2 years, 2 to 3 is my. I don't think that's pie in the sky. I think that's reasonable.
Thanks, John. Sorry. It's always been an interesting topic for me. We've got about 3 minutes. I'm just wondering if who hasn't spoken in this session. Nushan, Michelle, Nathan, did we hear from you any perspectives? I mean, everyone, the presentations were all fantastic, really interesting. If
I could just briefly go, just
Please
following
go
on about the carbon and the measurement of it, I think it applies to many other things too. So if we want to move to a natural accounting system, then we need to measure lots of stuff. We need to measure, you know, the shade that's being provided, or as well as the carbon. And, you know, so there's a lot of potential links to environmental accounting and business systems and financial systems that support nature-based solutions for climate change. So I think there's a lot of opportunities there.
Yeah, that's a really good point. I like that point very much. That's a good point. Yep, very clear, explicit. Anyone else? Nushin, do you have any perspectives?
Nothing to point out. I think all these, it was a very great conversation, and I think there are so many, as Nisha said, there are so many opportunities, and it's quite interesting to see that here in Australia, and especially in NSW, we have such a strong team of experts working on very different types of sensors. So yeah, for me, it was a very, I'm very hopeful and very optimistic of future, hearing about all these amazing research that is going on at different universities in NSW.
Very good, I agree. Subhas, we heard from you on measuring rainfall. Is there anything missing there? Any opportunities for other sensors?
Yeah, I think one thing that we researchers are always excited to develop new sensors and other things, but what is missing is that the community engagement. So for example, agricultural aspect, if we say that our sensor can measure something, but actually these farmers or the agriculture or common people, they need to understand that what is the effect of that. So that link, unless we, that gap, unless we bridge, it will be very difficult to achieve whatever we are talking about, the 2050 carbonless or whatever it is. So that part, I think, it is not the responsibility of the politician. It's also responsibility for us, the researcher, the scientist, to bridge that gap.
Good one. We capture that. Sarath, any perspectives from you?
Yeah, sure. I pick on John's comment on very expensive sensor versus not so expensive many sensors. I think these sensors has to be fit for purpose. And then they have their own space. So even the data analytics and machine learning algorithms can drive those selection of the sensors and which sensors to use basically, and what sort of a data to be acquired. So in that sense, I think we need a spectrum of sensors which are very cheap and measure some sort of measurements. At the same time, very expensive sensors which can give more information, and the information that cannot be captured using those cheap sensors. And in a data fusion sort of a framework to identify which sensors to be used and where to place, and also to make informed decisions about it.
Good, Sarah, perfect, thanks. And that now brings us to 11:53, which is perfectly timed for me to thank you for your wonderful contribution and your input. And I will pass over to Julian to give some closing remarks, and look forward to engaging you all in the follow-up discussions on this initiative. Thank you. Over to you, Julian.
Thanks so much for to Ben for chairing such a high-speed, high-energy discussion in the last half hour there. Obviously, there's a lot still to do, but it's really inspiring just to hear how much smart sensing has to contribute to understanding and mitigating the effects of climate change. I think based on the speeches and the discussion, NSSN now will develop from this event, as I mentioned earlier, a manuscript, a white paper, and a thought piece. So please look out for follow-up about that. Please remember also the upcoming Grand Challenge Fund call should be probably out in just a few weeks' time for any collaborative projects, and I can feel that there are some coming together from this roundtable as well. Finally, I'd really like to thank all of our roundtable participants for their great speeches and for the vibrant discussion. And also just to thank all of the NSSN team, so capably led by Nick Haskins, for all the organisation to make this happen. Thank you all, and I hope you have a great remainder of the day.
Thanks, Julian. Thanks, Ben.
Thank you, everyone.
Thank you.
Good
Bye.
stuff. Stay tuned. There'll be more.
Thank you.
Thank you.
Great to see
very
everyone.
much.
Thank you. Thank you so much.
Look forward to seeing you all again soon.